morning. Let's continue on the lecture Laplace transform. Okay, we're going to look at a very special application of Laplace transform. And this is about using Laplace transform to solve second order non-homogeneous ODE. Okay. So basically, it's an alternative way of solving ordinary differential equation. Now I'll show you an example first, and then we'll look at some of the specific scenarios. Okay? Yeah. Now to use the Laplace transform, you will actually make use of the Laplace table. Okay, some of the properties in the Laplace table. So let me open the table here. Okay. So we're going to use this. Okay. Yeah. So let's say we're going to solve this second order non-homogeneous ODE. So here is a non-homogeneous ODE because f of t is in present at here, and a couple initial conditions are given. Okay. So how do I solve this? I'm purposely leaving f of t here as a general function f of t without giving it a specific value, okay, or functions. Okay. Now we're going to solve this using a Laplace transform. So in particular, we're going to use some properties here. Okay, so this is what we're going to do. We're going to take Laplace transform, okay, of both sides of equation. Okay. So take Laplace transform both sides of the equation. For y. For the left side, basically you're taking Laplace transform y double prime plus 4y, and then Laplace transform f of t. So that's what I mean by taking Laplace transform both sides. For the right side, okay, we don't have the function given, but if the function is given, then we're able to find its Laplace transform, capital F of s. Okay. For the left side, Laplace is linear operator, so basically you're taking Laplace transform, okay, of individually like that. You can also take the 4 out of the bracket. Okay. Okay, so that's what happened on the left side. So what is the Laplace transform of y double prime, right? And what's the Laplace transform of y? So this is where we make use of the property. If you recall that, this property. So when you have a second order derivative, its Laplace transform is this expression. Right? So s squared capital F of s minus s times initial condition minus the derivative at the initial value. That's basically this one here. You change the f to y, right? That's what this one. Okay? Yeah. So for this one, we have s squared times capital Y of s minus s times y of 0 minus y, okay, prime at t equal to 0. And for this one here, that's not much you can do. So just 4 times capital Y of s. Okay. Remember, the objective is we're trying to solve for y of t. Okay, that's what the objective is, solving this ODE. And the other side, you keep it as capital F of s. Okay, so we have initial condition here. Y naught is 3. Y prime of naught is -1. So I'm going to plug it here and here. Okay. So remember, each term where they are from, like these 2 terms, right? These 2 terms they're from initial condition. Okay. So if initial condition is 0, then these two terms will actually be 0, right? They're not going to exist. Okay. So let's keep doing here. So then you get combined terms here. So you have both of these have y of s here. So we have s squared plus 4 capital Y of s. That's these two terms. And then the other two terms added here coming from initial condition. So y naught is 3, so 3s. Y prime naught is 1, so that's 1. Okay, so always remember, these two terms again from initial condition IC. Okay, this is from initial conditions. The rest of the term, like these two terms, s squared plus 4 squared, okay, they are actually come from where? They come from your original ODE. You see the coefficients, here's 4, and this is y double prime. And s, if you recall at the end of the lecture, when you learn Laplace, the s in the s domain basically represents a derivative action. So s squared represents what? A double second order derivative action. 1 over s is what type of action? Integration action, right? So that's the difference, in the time domain, this is a derivative. But in the s domain, which is basically after you did the Laplace, s times anything represents a derivative action, right? And anything divided by s represents an integration action. Okay. So now I'm going to combine things together. So we're going to solve for y of s. Okay. So from here, we're going to solve for y of s. Okay. You move the 3s and 1 to the right side, and then divided by s squared plus 4. Okay, so 3s plus 1 plus capital F of s, and divided by s squared plus 4. Okay, so that's your capital Y of s. Now why do I need this? Because remember, the idea is to get y of a t, right? The solution for y of t. But now I got capital Y of s. So the idea is, if we can take the inverse of this capital Y of s, Laplace inverse, and that's your y of t, right? That's your y of t. Okay, that's the objective. Okay, so how do I get the inverse? To get the inverse, I'm not going to ask you to do a hard integration to get the inverse. There's a formula. You can do an integration inverse Laplace transform to get the inverse. But we use the table. Okay, we use the simpler approach. To use the table meaning we have to use the simplest format we can find on the table. So coming back to this equation, to this function expression here, I will express this one into two parts. Okay, so we'll express this into two parts here. And then the first part, I don't think is simple enough, so I'm going to express that a little bit further simpler. So make it the first one 3s over s squared plus 4. And the second one is 1 over s plus 4. And then f of s over s squared plus 4. Yes? Oh, plus 1, yes, of course. Oh, sorry. Yeah, where did I made a mistake? Oh, this y prime is -1. Yes. So y prime -1, so this is a plus 1, and then this is a -1, then -1. Somehow I converted myself back to the track. So anyway, so this is a -1. Okay. Yeah. Okay. Now this is as simple as you can make it. Now if you have the capital F of s, then you might have to make some changes to this term. So we'll leave this term as it is, okay? But now I'm ready to take the inverse Laplace transform based on the results at here. So inverse Laplace transform meaning inverse Laplace transform each one of the term. For the first term, I look at this is how you do. You look up a table. Look at the table here. So if you look at this one here, whenever you have a s over s squared plus omega squared, the inverse is cosine omega squared, right? So the first term at here, what's the omega? 2. So the inverse of the first term is 3 times cosine 2t. Okay, that's the first one. Second one at here, I want to use a table, right? So let's go to the table here. Unfortunately, you don't have 1 over s squared plus 4. Let's say omega is still 2, so this is 2 squared. Okay, it's still 2 squared. But in the table, you don't have 1 over s squared plus omega squared. What you have is omega over s squared plus omega squared, right? So what do I have to do? I want to use this one here, okay? Now this is the closest I can make use of. So what do I have to do? I'm going to change this to 2. So then 2, that's exactly the same as the table now, right? And then what do I have to do? I divide it by 2. Okay? So now I have exactly what I need from the table. So the inverse for this one is 1/2 sine 2t. Okay. Right, so that's give you a sense of how you can find the inverse Laplace using the table. Okay. The last one at here, okay, we can't do it much about it because we don't know what the function f of t is. Right? If you do have it, then you can actually do something to it. But however, I want to point out is this. So if you look at this term at here, okay? If you look at this term here, it's f of s. Basically, this term here is f of s times 1 over s squared plus 4. Okay. So it's like there are two s functions multiply each other. So we have a f1 function is f of s, another function is 1 over s squared plus 4. Okay? Yeah. Now in the previous lecture we learned another application of Laplace. The other application of Laplace was when you have a Laplace of a two-time function f of t convolute g of t. What does it equal to? F of s times g of s, right? Yeah, that's another application of Laplace. So if I make use of that property here, look at this. When you have two s functions multiply each other, then its inverse Laplace should be the time function for this one, which is f of t, right? That's the input, times the inverse Laplace of this one, which is basically very much like this one here. So that's essentially 1/2 sine 2t. So this term basically is the input convolute 1/2 sine 2t. Okay? Yeah. So if I have, now typically when you have a function f of t, you actually don't need to do this step, but I need to show you the relationship at here. The detailed work should be over here, find the inverse Laplace and then find the t function. Okay. A little bit further observation, okay? A little bit further observation here. Remember I purposely highlighted the terms coming from initial conditions. So these terms from initial conditions, this term from initial condition, this term from where? Initial condition, right? So these two terms from initial condition, the inverse Laplace, these two terms, they are contributed from initial conditions. So if you do a tracking, right? If you track where the part of the solution comes from, so within the solution for y of t, part of the solution, these are contributed from initial conditions. So they're contributed from initial condition, and these two, right? They're not coming from initial condition. Where are these two from? This is f of t. F of t is the system input. So they're not from initial condition, right? So this is not from initial conditions. They're from the forcing term. They're from the input, the actual forcing input into the system. So the solution, if you look at the solution of this y of t here, this is actually a general observation. It always has two parts. One part contributed from initial condition, and one part contributed from the forcing term, the forcing input into the system. Okay, and that's always true. Now imagining, right, if your initial condition is 0, then you're not going to have these terms here, right? If initial condition is 0, these two terms 0, then you're not going to have these two terms. You're not going to have these two terms. So you will not have this part here. You will only have the contribution from the forcing input, right, from external input to the system. Okay. So that's the nature, right, of this a general solution of a ODE here. Okay. But if you look at the way we're doing here, right, we're focusing on the application of the Laplace transform to solve ODE. So the idea is you're not solving it in time domain, you're converting it into the S domain using Laplace. So everything is in terms of S now. And now within the S domain, the manipulation wise, right, there's no integration, right, and it's all about basically some multiplication, division, okay, some manipulations that are here, algebraic manipulation. And then you take using the table, right, to find y of t. Okay. So essentially this process is sort of like a detour, right, compared to the time domain solution. The detour is to use the S domain, which is the Laplace approach. But you have to make use the table to simplify it and then to find the solution. Okay. Just going to do it here. Yeah. Okay. So that's the idea of using Laplace transform. So here is a flow chart I wanted to show you it here. If you start from an ODE, okay, we take the Laplace transform. Okay. Once you take the Laplace transform, okay, by considering the initial conditions and making use the property of transforming, how do you transform a first order, second order derivative using the property, you will be able to obtain an S function for y of s. Okay, so y of s is the output, right? Is the system output that we're looking for. And then from here, you were going to have to, most probably you're going to have to do is, you're going to have to decompose this y of s. We have to make it as simple as possible. So we're going to decompose this y of s into the simplest form. Okay. How simple? As simple as you can make use the table. Okay. You don't have to be any simpler. Okay. Just have to be simple. You can make use the table. Okay. So this part at here. Okay. Maybe we should put it in brackets. Sorry, let me put it in the bracket here. Okay, so that's what happens this step here. Okay, I'll show you a few techniques how to decompose this y of s into the simplest form. Okay, this is where we're going to focus. Once you get the simplest format, and then you can use the table now. Use table to find inverse Laplace, which give you this y of t. Okay. So that's why they call it detour, right? I think in the previous lecture what we learned, you have a time domain approach. Okay, there are different approaches. There's a method of undetermined coefficient. There's also variation of parameters. Okay, so you can use time domain approach to get y of t for sure, but this time you're using Laplace transform, okay, to get y of t. Okay. So that's the general bigger picture, what we're doing at here. Okay. So this y of s, okay, so from here at this step here, we said obtain an s function, right, for the y of s. So this y of s function, if you look at this one here, it's going to be in a fraction format. So there's a numerator, there's going to be a denominator. So that's basically what the s function is in general format for the y of s. Okay. So this is going to be in the numerator and a denominator. Okay, so for y of s, then for this step here, you're decomposing it into the simplest format. So the technique is, how do I decompose a fraction into the simplest format, right? So that we can make use of the table to find the inverse Laplace. So before we go ahead, and then I want to introduce a new concept. Okay, if I have a fraction for y of s, okay, now if we set this numerator, if we set the denominator to be 0, okay. So if we set denominator to be 0, the solution for s, okay, is called, most probably you have more than one solution, so I should say solutions. Solutions for this s you get is called poles. So when you set the denominator to be 0 and solve for s, you get certain solutions. Those solutions are called the poles of the system. Okay. Single most important concept when you learn a control system, basically. Okay. The poles of the system determines the stability of the system. As you're going to see, actually, the d of s basically is the characteristic equation of the system, right? So you can see what's the d of s in the previous example, s squared plus 4, right? It's like what? Lambda squared plus 4. Remember, right? That characteristic equation. Okay, we just change the lambda to s. Now, if you set the numerator to be 0, and then you will get some more solutions for s, and this time they're called, okay, zeros. Okay, so solutions for numerator are called zeros. Solutions for denominators are called poles. Okay, those are basically a simple concept. Okay, yeah. So now I'm gonna show you, okay, given different types of y of s, how do we decompose it? How do we find the inverse Laplace of that? Okay, yeah. So let's start from the case number 1. Okay, we call that simple poles. Okay, simple poles. So this one takes the y of s takes the format like this. You have a numerator at here, and the denominator, okay, can be written in the following format. there. So denominator can be factored, okay, into many small terms. S plus P1 times S plus P2 and up to S plus Pn. This is what we call a simple pose. Because why? Because if you set the denominator to be 0, then you get a solution for S. One is negative P1, negative P2, up to negative Pn, right? So those are the poles. And assuming all the poles are distinct from each other. Okay, so P1, P2, Pn, okay, they're distinct from each other. Now you get this simple poles basically. Okay, right. So you can write down what the poles system are, right? Yeah. Now if you have this kind of format for y of s, then what you do is you decompose this y of s into the following term. So this one can be decomposed into a constant divided by this, another constant divided by this, and up to this. Okay? Yeah. So that's, you can decompose your y of s into all of these simple formats here. So why is this going to be useful? Because if you can decompose this into this format, right? If you look at the table, I can use that particular term to find the inverse, right? 1 over s plus a has inverse of this, right? That's basically exactly in the same format. Okay. So the question is, what will be the values for all the constants k1, k2, and kn, right? Now remember, your k1, k2, kn, okay, is not an arbitrary value. When you put these terms together back into the fraction format, this should give you back this denominator n of s. Okay, that's the idea. Okay. To find, I'll give you two options. Okay, to find the ki, you have two options. Okay, one is to use formula, and this formula here for ki says this. Okay. This is your ki. To find, for example, to find k1 or to find k2, so you need to use the denominator associated with the k2, and then times y of s, and then set the s equal to negative p2, okay, to find the value of k2. Okay. So I'll show you an example here. Okay. So let's say, suppose we got y of s, okay, equal to s squared plus 12 over s plus 2, s plus 3. Okay. Let's say you have this particular y of s somehow from your Laplace transform, right? Yeah. I'm skipping a step here just to give you assumed results. Okay. So basically, somehow from here to here, you get your y of s, okay, is this one here. Okay. So the bottom here is d of s. Apparently, this is exactly in the same formula. When you set the bottom equal to 0, you got s equal to 0, s equal to negative 2, s equal to negative 3. So there's 3 distinct poles, and this is in the simple pose format. So we can separate this fraction into 3 terms. Okay, k1, k2, and k3. Is it good so far? So good? Yeah? Okay. Now let's use the formula to find k1, k2, k3. So what's k1? k1 equal to s times y of s, and then let s equal to 0. So s times y of s, and this is y of s here. And when it times s, the bottom s and s cancelled out. You get s squared plus 12, s plus 2, s plus 3, and then let s equal to 0. Okay. The reason you had there's a reason why you times s or s plus pi first, right, before you let s equal to negative pi, because the formula won't work, right? If you don't do this step, if you directly substitute, for example, here s equal to 0 back into this, then you got something divided by infinite, right? By 0, right? Then you got an infinite. Okay. So once you get s equal to 0, plug it in. You got 12 over 6, which is 2. So that's your K1. Okay, try yourself. What about K2? What about the K3? Okay. Give yourself a few seconds here. Let's see if you can get K2. And K3. Okay, so what do you get for K2? 4.3. Okay, negative 8 though. What do you get for K3? 7. Yeah. So give it a try, huh? Yeah. So that's K1, K2, K3. So finally your y of s equal to 2 over s plus, not plus, no, it's negative 8 over s plus 2 plus 7 over s plus 3. And you can, if you're not too sure, you can always double check, or you can always put this 3 back into the fraction, and then you should get exactly the same as the original numerator. Okay. So now we take the inverse Laplace. And this is the time you start to look at the table. So what's the inverse Laplace of 2 over s? The inverse Laplace of 1 over s is u of t. So 2 of s is 2 times u of t. And the Laplace transform of 1 over s plus a is e to the power negative at. Now if you remember, I mentioned this in the table. I didn't write u of t for each one of the results. So technically you have each one of the function times u of t times u of t. Okay, so that's technically what's going on here. So this one is a times e to the power negative 2t u of t, and this one is 7 times e to the power negative 3t and u of t. You can take the u of t out. That u of t here basically serves as a meaning that you got a causal function. Okay? So there's nothing when t is less than 0. Right? So that's y of t. Now if you think about it, if you have an ODE in that type of format, it might actually quite difficult to solve using time domain. Okay. Okay. This is approach using formula. This is a formula here. If you feel comfortable with the formula, you can always use the formula. There's another approach is comparing coefficients. Okay. Now this one, okay, does involve a little bit computation, a little bit more complicated than the formula. But I wanted to show you here, it is one approach to do. Comparing coefficient basically means you will write back into the fraction format, okay, from here. So K1 s plus 2, s plus 3, and then k2 times s, s plus 3, and k3 times s, s plus 2. So when you put it back, right, it'll look like that. Okay. Then you expand the numerator, expand them out, okay, and group similar terms. So when you expand all those the numerator out and group the similar term, you got s squared here, k1, k2, k3 plus s, 5k1, 3k2, and 2k3, and then plus 6k1. Okay, so that's what it looks like if you expand, group all the similar terms, and you get this. Okay. So what am I comparing? The numerator at here, right, should be the same as the numerator from original y of s. And the original y of s numerator is, what's the original one? Is s squared plus 12. Okay, so this one should equal to s squared plus 12. Now you compare coefficients. The coefficient for s squared, k1, k2, k3 should be 1. Right? Coefficient for s, there's no s term, so that should be 0 there. And constant term should be 12. Here. So now you got 3 equations, 3 unknowns, and you can solve for k1, k2, and k3. So k1 is 2, k2 is negative 8, and k3 is 7. That should be the same answer as using formula. And then you can proceed to get the inverse right from here. Okay. So that's comparing coefficients approach. Yes?
So is it possible to use either way for these kind of problems and will work for any of the problems?
Yes. Yeah. Particularly sometimes it's actually like this time, this one has 3 terms here, right? When you have just 2 terms, it's actually probably simpler using this comparing coefficient sometimes. Yeah. Okay, that's case number 1. Is that when you have just simple poles, okay, on the denominator. Okay. The case number 2 is when denominator has complex conjugate poles. Okay. Complex conjugate poles. So when you set the denominator to be 0, and you end up with a solution that's actually complex conjugates. So this is the number 2 case. So I'll give you an example here, okay? So let's see, we have a y double prime plus ay prime plus 25y and equal to 20 times e to the power of a negative 3t. Initial condition, y of 0 is 0, y prime of 0 is 0. There's no initial condition, it's all 0. Okay. And I want to solve this one using Laplace transform. Okay. So if you look at this one, if you solve using time domain approach, the first step is always to get the characteristic equation. Right? And this characteristic equation will give you complex conjugate poles, basically. Okay. But I'm solving using Laplace, right? So basically we're taking Laplace of both sides. Okay. And once you've done the Laplace of both sides, here you get s squared capital Y of s minus s times y of 0 minus y prime of 0 plus 8 times s y of s and then minus 8 times y of 0 plus 25 y of s, and the last the right side is 1 over s plus 3. Here, okay. So all of these are directly coming from the table, right? So when you taking Laplace transform of a first order and a second order derivative, this is the results of the transform. Now because initial conditions are all 0, so I don't have the 3 terms over here, and I will have only a terms here, y of s, y of s. So we can put the y of s term together. Okay, so you get this. So now you see actually that term over here, right? It's very much like the characteristic equation, right? It's basically the same. If you change s to lambda, you get the same characteristic equation. Okay. So your y of s is what? Is 20 times 1 over s squared plus 8s plus 25, and then s plus 3. Okay, that's it. That's the expression for y of s. Okay. So from here, you have a numerator divided by a denominator, and then you try to decompose this expression into the simplest format. And before you do that, right, we examine the solution for the denominator. The solution for the denominator, this one is easy. That's s equal to negative 3, right? But if you set s squared plus 8s plus 25 equal to 0, you're going to get a pair of complex conjugate poles. And that's basically the case number 2. So in this case, okay, you keep this term as it is. You don't break it down into any simpler format anymore, because you can't. You can't break it down into multiplication of 2 factors anymore. Okay? So what you do is, from here you do a fraction expansion. You have a over s plus 3, right? That's basically a term associated with that. And then you have a b over the s squared plus as plus 25. A bs plus c. Okay. So basically, what I'm doing in here, you see here, the a is a constant associated with that s plus 3, very much like the case number 1. But for the other term, s squared plus as plus 25, your numerator here is bs plus c. Now you can't change this, okay? Just remember, this is basically like a rule. So when you have this term here is complex conjugate roots, then you decompose this term into 2 terms. That term associated with the s squared plus as plus 25, the numerator has to be bs plus c. It has to be. Otherwise, it's not going to work. Okay. So this is basically 1 order less than the s squared. Okay. So now the question becomes, what is a, what is b, and what is the c? Okay. Now I'll show you why. You might wonder, why is this simpler, right? Why is this actually going to help us in terms of finding inverse Laplace? So it will work. Just hang on a second here, and you'll see the reason. Okay. But now let's find a, b, c. Okay. So to find a, b, c, we use comparing coefficient approach. So this time you don't really have much of a freedom. Your freedom is comparing coefficients. So what does that mean? Basically means you will write these 2 fractions back together. So you get a times s squared plus as plus 25 here, then plus S plus 3 times BS plus C. So put it back into one piece. So extra careful, right? When you do all of this, every calculation, be careful, right? Don't make any mistakes. One little mistake will lead to the rest of the mistake, okay? So then we expand the numerator at here and also group similar terms. Okay, group similar terms for the numerator. Okay, so what I'm gonna get, if I expand it and group the similar term, I get a plus b s squared plus 8a plus 3b plus c times s 25a 3c. Okay. This is the numerator. It's all algebraic calculation, right? There's nothing tricky at all. You just have to be very careful. The numerator at here has to be the same as the original numerator. What is the original numerator? Original numerator is 20. So now you compare coefficients. What is the coefficient for s squared? A plus b. Is there any s squared? No? Yeah, 0. What's the coefficient for s? A8 plus 3b plus c. Any coefficient on the other side? No, so 0. So last one is the coefficient for s to the power 0, which is 1. That's 25a plus 3c. Now this one equal to 20. Okay. So 3 equation, 3 unknown. Use substitution rule to solve for a, b, c. So a is 2, b is negative 2, c is negative 10. Okay. Put this a, b, c back to your y of s. So y of s is 2 over s plus 3 plus bs times plus c. So bs is negative 2s, and then minus plus c is minus 10 divided by s squared 8s plus 25. Alright, so up to here you feel like, oh boy, am I going to finish? Almost, but actually the next step is a very critical one. The next step is to take inverse Laplace. The first term inverse Laplace is very simple. Yes? Sorry, what's that? No, bs plus c. So b is negative 2, c is, Okay, so inverse Laplace, the first one is pretty simple. The first one is negative e to the power of negative 3t, right? That's pretty straightforward. So what is inverse Laplace of negative 2s minus 10 s squared plus 8s plus 25 then? Okay. So I don't have time to do this now, but I'll give you a hint at it here. I'm still going to use table, right? So if you look at the table here, okay, which one is the closest to what we have? These two. So you see these two at here. If you set the bottom of these two, you get imaginary solution, right? Complex solution. So we need to make use these two to get inverse. So I need to do something to this term to write it in this format so that I can use the table. So I'll show you how to do that. And that's basically the tricky part. Okay. So I'll show you in the next lecture. Okay. And the other thing I need to say is we have 2 more quizzes to go. So we're going to use the last 2 weeks to do an exercise. Okay. There'll be one question will be on the solving second order ODE using a method of undetermined coefficient, and the other one will be solving ODE using Laplace as we're doing right now. Okay.